Okay, so today I'm going to be talking about the library called Scalaz, which you might have heard of already. It's this sort of popular functional programming kind of example, sort of, I don't know how to describe it. It's a sort of library with lots of juicy best practices that you can use when you apply functional programming in all its honesty in a way. And the way I want to do this is I'm not going to go through a lot of Scalaz code, or I mean, I'm going to show you code, but I want to get the sort of principles across, like the idea behind it, why you should use it, or when it makes sense to use these kind of ideas in Scalaz. And there's 4 topics I sort of chose. I mean, there's much more in Scalaz than just that. And type classes, for example, is not even a Scalaz thing in a way. It's just this, I don't know, like a different approach to polymorphism. Lenses, I'll just go for it one by another rather than. And it's not a very structured presentation, as you can see, just 2 slides. I'm just going to go, the way I'm going to do is I'm just going to go through blog posts, which I find interesting for that topic. And the first thing I'm going to start with is Heiko's blog, which explains type classes, I think, very neatly.
You will provide these links later.
Yeah, I can give you all these links. So type classes, or maybe I'll go to the Scalaz thing first. So there's this really nice tutorial called Learning Scalaz, which sort of describes most of these things. And we're just going to go through that one by one in a way. So the thing with type classes is you can
make it much bigger, please.
Much bigger. Much bigger. More.
Yeah. More.
Okay. So the thing with type classes is it's sort of a different take on polymorphism. You might know sort of different ways of implementing polymorphism from other languages. So like, for example, in C++ you can use meta templates or runtime types, as in like the sort of virtual methods to implement polymorphism. It's both polymorphism in the sense that you can change the behavior of certain things in a way, and you don't. It's transparent to you, to whoever's using it. Like, for example, if you say you have this is sort of polymorphism as well. When you say you define a method head, which takes a list and just returns the first element. Whatever the type A is, it just works. It doesn't matter. Like, you can work with ints or cars or whatever. This is a kind of polymorphism as well. There is the subtype polymorphism, which...
Excuse me, are you okay with questions?
Yeah, sure.
Where is like some dynamic change on type? In the generics, there is no change. Just
well, this method can work with any type A. That's the...
type, so there is no... So why is it on the list of polymorphism?
Because
it doesn't care for the type, right?
Yeah, polymorphism just means that it works the same with different types. It doesn't need to be, you don't need to change the type at runtime. That's not...
Okay, so it works the same for different types.
Yeah.
Usually
Or,
what I thought is that polymorphism means it works different for the same type, like subtypes.
different for the same type, but...
Well,
What's-
it's late binding, in fact. I don't see any late binding here. But it's just a definition, so it's okay.
Yeah, okay, yeah. Maybe it clarifies itself later on as well, because now we're going to come to this subtype polymorphism, which is you can call this plus method on any type A which implements the plus trait. That's your kind of polymorphism in a way. But again, like the sort of late binding thing, I always say that, like, that's the difference between static and dynamic polymorphism, but you only need that difference in languages with weak type systems, in a way where you lose the types. Like, if you use generics all the way through, and you never throw away its original type, then it's actually, you choose the method you want to execute at runtime, at compile time, and you don't need to. It behaves the same, but you choose the method at compile time. And this is the sort of Scala set approach, or it sort of comes from Haskell with type classes, where you don't insist, and there's a special syntax for this in Scala, you don't insist on a type to implement a certain trait or to implement a certain interface. You just insist on there being something that converts that into something that implements that interface. So this is what this implicitly is about. You sort of take an A and convert it into something that implements this plus, and then you can call the plus method. And this might seem like horrible syntax now, but it is really, really helpful when you start composing these kind of things. So like, for example, say you want to have a plus, I mean, this is going to go into monads now. You want to have this thing implement a plus trait, which just adds two things together. And you also wanted to implement minus, or not a minus, let's say a zero trait, which just, for the type, it returns the default element. So if we're talking about integers, plus just means to add two integers, and the zero trait returns the integer zero. I mean, I can't write it down anywhere, but I'm just gonna maybe
it's worth mentioning that
Yes.
this syntax is a nice feature of Scala for hiding the implicit parameter.
Yeah.
It's
Here it is. It's sort of equivalent to writing this in a way. I mean, it's just this cryptic parameter, but you have this parameter lists with two A's and something, another implicit parameter, which implements this plus interface, and which you can use to map between those. Okay, so maybe that's enough for that. Now let's go to the example that Heiko gives. Sorry. Okay, so we're gonna increase this as well. Sorry. Okay, so can you read this?
Okay.
Is it okay? Okay, so the objective in this example is, oh no, we're way up. Okay, so what we want to do here is we want to define an equals method, which is type safe. So at the moment, if you run, say, 1.equals foo, it compiles, because equals is defined to take any. But it might not make sense to compare an integer and a string. I mean, it would return false, but you actually might want the compiler to complain about these kind of method calls. So what we want to do is we want to define a type safe equals method. And we're going to do that using type classes, in a way. I mean, this is the sort of pattern behind this. And how we're going to do this is we're going to define an implicit class, which is sort of another Scala feature, where you say this equals trait takes some element as a parameter, and then defines the method like 3 equals, to take another parameter of that type, and then just does that. It looks pretty much the same, as in like you're still just comparing left and right using these 2 equal signs. But the beauty of it is that now it's type safe in a way that like 1, 2, 3 equals, 1, 2, 3 returns true, this returns false, and this doesn't compile because the types don't match.
Why is it type safe now?
Why is it type safe now? Because it's implemented in a generic way. So it works for any type A, and then it knows how to convert any type A into something that implements this equal trait. Okay, so far, I mean, what this is defining sort of trait, which is called equal, and it also defines the conversion from any type A into something that implements this trait. And now this trait is defined differently than the normal equals method. Like here you have equals other any, because you can't define it anywhere else. But here, you now know the type A. So you can use that type in the method here. Yeah, and that's why it's type safe now. Okay, and like, I mean, there's other things you can do now. This is the first part. And now, like, he has some more examples. As in, like, he builds upon that. Because you can think about implementing type safe equality as well in terms of like if there's an implicit conversion to something. All right, I think I'm getting too far here. I don't know. I'm just gonna skip this part now. But I don't know. There's like so many things you can do with type classes, and we're gonna see something more later on with monoids.
So is this a type class now? Or is this just an implicit trait?
So I mean, there's no such thing as a type class like in the language itself. It's type classes exist in Haskell, and Scala now has means of mimicking that in a way. Yeah. So equal this thing here would be called the trait. What you call a trait in Scala would be called a type class if it follows this sort of implicit conversion pattern. You don't actually ever implement that trait directly. Like you never write class A : equal.
Understand, because it's implicit. So every left that implements equals can be converted to this implicit.
Yeah,
class.
exactly.
So that's the point. So this and all classes that implement this exist in the type class, so like the class of all same types.
Yeah, and that's
for understanding.
Yeah, and that's the sort of power of type classes in a way. Like you can define an interface and an implementation for a lot of different types in one go. And
for a whole class of types.
Yeah, exactly. And that's why it's called type class, actually, because you define it for like that. Yeah. Okay. So, what was the next part? Okay, lenses. Yeah, I mean lenses are. Let's go here.
But one last question. But you need to import this, right?
Yeah, you need to import this. Yeah. Otherwise, it wouldn't find the implicits.
It's the 11.
Everybody knows here what implicits are?
Okay, so lenses, this is now sort of just a neat kind of thing. It's not a sort of fundamental design principle in a way. It's just the best way to describe it is like this. When you this piece of code shows it. When you have, like in functional programming, you're supposed to write immutable data structures. Like whenever you modify something, you create a copy and you return that copy instead. Now, if you do that, it can become quite tedious to actually modify something like deep down in a hierarchy or in a sort of bigger data structure. As you can see, like if we want to modify that E, we actually have to create a copy of that E, and then everything, like we have to create a copy of everything above it as well. It sort of, it propagates. Now, the nice thing, and this is what lenses are for, like amongst other things, but the lenses is, where is a good definition? Okay, yeah, let's just take that. So, a lens is a pair of functions which you pair a getter and a setter together, so that, for example, here you take, this is the setter which updates the position of a turtle. You get a turtle, a new value, you create a copy of that turtle and update the position to the new value, and that's the first function. That's the setter. The second function is usually much easier because it's just a getter. So you just return the position of whatever you get. That's the two functions. Just a setter and a getter. And the nice thing now is that you can start composing these pairs of functions, because whenever, like,
Excuse me?
yeah,
This underscore dot position,
yeah,
does this now operate on the copy or on the original?
this is just a shorthand for writing a this function error and a dot position. So it's not it doesn't operate. It doesn't relate to this at all. This line is completely separate from this one. This just defines another function in a very short way. This, I mean, the function it defines is it takes a turtle and it returns its position. So it's get position in a way. Just
How do we know the underscore, what the underscore stands for?
it's inferred from this type up here.
Mm-hmm.
So the first type argument in here is the first type here. I mean,
Just scroll up on the function definition of apply.
yeah,
The one on
Yeah.
top. If you look at the apply,
maybe.
you see that it takes two functions. The first is, or it takes as first parameter f from a to b, which
Yeah.
is a function.
So I mean,
It's just a signature.
let's just use this that apply. I mean, this would be an object. So the first function it takes is, so it takes two functions, a t, which, and then, sorry, it's difficult to write when you're not looking on the keyboard or on the screen altogether. It takes a t, the setter. Okay, now I need to, a t, an s, which is the value you want to set.
Can you make it bigger?
I'm not sure if I can make this bigger, to be honest.
That's Mac, right? Sorry.
So,
Function scroll
Yeah.
up.
Wow.
Wow.
okay, so it returns another t. That's the function. That's the definition of this function, and the getter takes a t and it returns an s. Does that make sense?
I think people don't know the current version of the signature. The T to S to T, which would be this notation. I think it's maybe a bit confusing.
I'm to be honest, I don't know the proper notation. I mean, I'm just mainly using Haskell, and you can.
It just put parentheses around them and a comma in between T and S.
Parentheses around T,
Just a signature. It's okay. We can look.
T, yeah, parentheses there, and
Around
S, yeah.
Here?
Yeah.
Here as well? Or?
No, no.
No,
Yeah.
Okay.
And what does the by function return?
It returns an instance of a lens.
Okay.
I mean, this is actually sort of, you need to think about it this way. So there is a lens, yeah, I mean, I don't want to go into the details of like how it's implemented, I just want to get the idea across. So this, I mean, if we go back to the example, we're not actually calling the apply method here, we're calling the lens U, which I mean, there's different lenses, there's lenses for monads and whatnot, but this is the, lens U returns a lens and that apply takes two, yeah, okay. Never mind, I'm just confusing myself now. Okay, now, and yeah, the thing is now you can start using these lenses to sort of compose them, so you don't have to write these copy things all the time, because you can actually like aggregate different lenses, and when you traverse down, you don't have to keep track of the whole structure. But okay, I think I'm just gonna go to the next one. This is, I mean, lenses are not that important. I thought it's sort of one of the easier things of Scala
Let's
sets.
see a usage, please, before you continue. Just show the usage.
The usage.
Show the usage, where we do not have this all this copy.
Yeah, how you can replace this copy, nested copies?
You can. So, for example, turtle X. Okay, so we have. Maybe this is a nice example. So you have the turtle. It has a point. Or maybe let's just go through these data structures first. Just briefly, how they are defined. So a turtle has a position, some kind of heading and a color. The point, so that's the position, has an X and a Y. And what we want to do is we want to take a turtle and update it, the X component of the point. That's this A.B.C, whatever. And the way we're doing this is, well, define a lens for the turtle position, which is, it takes a turtle and the new position, creates a copy of that turtle using the new position, that's the setter. The getter is just return the position. And we also define a lens for the X component of a point. So this lens now takes a point and the double, so it takes a point, a new value for the X component. It creates a copy of that point using the new value of the X component, and it just returns the X component. So that's two, I think, fairly trivial kinds of lenses. And the nice thing is, now we can compose them together. So we say if you want to modify the X position of a turtle, we just use the turtle position lens, followed by, or I don't know how to translate this into English, by the by the point X lens, which just makes sense in a way. You just compose these two lenses together, and then you're modifying something much more complicated. And that's actually how you should do it. Like you shouldn't define lenses for like anything. Like you shouldn't write a lens that does this. That would be pointless in a way. Yeah? And now you can, well, I mean, you could see with more complicated data structures how this simplifies the whole updating part a lot. Like, I mean, for example, suppose that at some point you decided to rewrite this so that it's not a case class anymore, but something else, in which case you lose the copy method. Or, I mean, if you don't define it yourself, and then you have to rewrite all the code that updates the X position or the Y position of a point, because you can't use the copy method anymore. It's sort of, lenses kind of hide the fact how you update or how you read. It just encapsulates getters and setters in a way.
Is it only for attributes or for anything?
Sorry?
Is the idea specifically for attributes or properties, or could it be for anything?
Well, anything where you have a getter and a setter.
Okay,
anything.
you always need to pair.
Yeah, you always need to pair, otherwise it doesn't work. Okay, so that's that. The next thing.
Excuse me, why do I need this? I mean, is it just to basically modify unmodifiable data somehow? I mean,
Well, it's just if you have a lot of this code, if your code looks like this, and like on a lot of places, you might want to look into lenses, but otherwise it doesn't make sense.
If you have a
Yeah.
data structure,
If you work a lot with immutable data structures, and you want to hide the fact how you update stuff, then you might want to use lenses. Otherwise, there's no point. It's just like the thing is, or
so basically it's somehow of a list that's composed of, at the beginning you have these data structures and then you have all the changes done to it.
yeah. I mean, it's just I think it helps to transition from the imperative to the functional approach. Like when you can't modify data anymore in the data structure, it does become tedious sometimes to update something in a nested kind of part of the data structure. And if like it's just a remedy for the tediousness of updating immutable data structures sometimes. That's all it is. Nothing more and nothing less.
Does it help me with then the composition of these functions, or is it just the idea that I use it because? Like
No, well, it does provide a few utility functions, like Scalaz said. Like the lens thing, you could easily define yourself. I mean, I almost did it, but then there's functions like this one, which takes two lenses and composes them together. I mean, you could easily define that yourself as well. If that's all you need, you don't need to use Scalaz to have this. This is just, I don't know, some best practices in functional programming. Okay. I don't know, any other questions? Or
So at the beginning there was the before sort of copy. Is there in this blog post somewhere the after state, the usage, how it improves your code, how it looks better? It would make your point clearer, I think, if you could show us.
it doesn't use this specific example.
That's a shame.
it's a
But
for function with the arrow. Just imagine the for function
Yeah, I
with
can
the arrow.
imagine, but I think it would be...
You need more imagination. Just make it up. Have some unicorns and rainbows.
Everybody's happy and dancing around.
yeah, no, it doesn't give this specific example anymore.
Could I abuse it to help me with general function composition? Would it be helpful? Or is it not powerful enough?
Why would you not just want to use function composition if you want to do
Because I
functional?
like this arrow and just put all my functions. I don't know.
Yeah, I mean you could. I'm sure there's something you can use to implement function composition using the arrow syntax like this. But if you do that,
Just a symbolic.
like you wouldn't want to use
So it
lenses
doesn't
for.
give me that.
No.
I think the keyword with lenses, I mean, I haven't used them, but I think what I took away from this, it should be nested.
Yeah,
I think the keyword is nested. It's
Yeah,
nested
it
data
needs to be
structures,
a
not for other composition.
Yeah, it needs to be a complicated data structure with lots of traversals down, and you want to hide the fact, or you want to get rid of like the tediousness of copying everything up to the root. Like for example, if you have say a huge MongoDB document or whatever, it's this sort of nested data structure, and every time you update something, you actually want to have a new version of that. And I'm sure people implementing these kind of databases, they use lenses. But yeah, I don't know. Okay, maybe let's just go on to The other thing I wanted to talk about just briefly, as opposed to a monad, is
My question is in regards to what's the use case or what?
we're gonna see use cases here, especially with monoids. Maybe I'm not gonna explain the difference now, but later on.
Okay.
So a monoid is, in terms of computer science, you can think of it as a data type which implements certain properties. So the usual example is integer. I'll just go through the rules first.
Okay.
It's an idea from discrete math, where you say a monoid is something that implements 3 rules, or it's a pair. I should have prepared slides.
Okay.
A monoid is a function and an element such that it implements 3 rules. Maybe I'll just start with the example first.
Mm-hmm.
A string is a monoid in the sense that you can add 2 strings and it still stays a string.
Mm-hmm.
No matter how you add strings, it's the same result in the end. And if you add a string to the empty string, it stays the same. So that's the 3 rules that a monoid needs to implement. It has, it's a type that implements some associative operation on that type. And there's a few properties that it abides by, like this associativity and identity. Okay, maybe just a few examples. So why would you bother about a monoid?
Exactly.
Yeah.
Because it's cool.
What?
Because it's cool.
Because it's cool. Yeah, because it's a hipster. So monoids appear a lot if you do map reduce. Basically, that's the point. Map reduce is this kind of framework where you process a lot of data, and in this example now, what we want to do is we have, say, 3 pages in a book, and we want to count the words in that book. And what we do is we define a function that just takes some text, splits the text, and then returns the length.
Mm-hmm.
So that's the function that we use to count the number of words. Now the thing, how is this a monoid? Because you could now that we have this function, there's 2 ways we could implement counting the whole book. Like this function just counts 1 page. We could append all these pages together. So like we could do a string append. So take the first page, append the second page, append the third page, and then run this word count method, which would work. I mean, it would return the number of words in the book. Or we could do it the other way around, where we say we count the words in the first page, we count the words in the second page, and we count the words in the third page, and then we just add them together. Okay, and so this is sort of map reduce in its simplest form, where we
The
say...
second one, not the first one.
Yeah, no, I mean, that this is reduced map, if you want it, but it wouldn't make sense. Yeah. The second one is map reduce, but the overall idea I meant. And you can only do this, like switch from this approach to this approach, if the underlying data type is a monoid. Only then are you allowed to swap those operations. So to give a counter example to make this clear, when you're not allowed to do that, say you want to count the number.
It's the mean for example.
Yeah, the mean, or this example uses frequency, or the most frequent word on a page. So now what do you have? Say you have this function that does whatever it does to determine the word that appears the most often in a page. And now you want to use the same pattern, but it doesn't work anymore, because if if you append those pages and then determine the most frequent word, it works. That's the same as before. But if you run this most frequent word operation individually now, it doesn't work anymore. And that's because most frequent word, the function, is not what's called monoid. It's not a monoid homomorphism, which means, this is now getting a bit complicated again.
It's a cool word. It's not. It's just a function from something to something. And
Yeah.
It's not
So
a function.
okay. So a morphism is just some function. This is just a fancy way of saying a function. A homomorphism is just a function that preserves the sameness of something. So whatever that sameness might be. And a monoid homomorphism is a function that preserves the sameness of a monoid. So if the input argument of the function is a monoid, the output argument of the function should be a monoid as well. Then the function itself is a monoid homomorphism. So so this is not an example of a monoid homomorphism. What you could do to fix this is to return a map instead, where you define like, well, the solution is like instead of writing a function that returns the most frequent word, you return a function that returns a map, mapping strings to integers. So you just return the whole thing rather than just the most frequent one. Because now, if you, it doesn't have code here anymore, I think. On this page it explains the same thing with average as well. Yeah, here. So, map. I mean, this is... yeah, so rather than doing the same thing, it just maps the input, again, using this word frequency function we defined, and then reduces the whole thing by adding those maps together. Now, the adding step is easy again because you just need to, like adding two maps can be done by just taking every key and sort of determining the values from both maps and adding those values together. And then the whole thing works again, because in the end, you're going to get this composed map which has the right answer. So you can switch.
The key thing about the reduce function is that if you have a large data set, and you took the example of MongoDB, it gets actually executed multiple times. So the reduce function runs on the result of other reduce functions. So that's why the input and the output must be the same, so that it can gradually reduce a big data set that is the result of the map functions into one aggregated result. So that's the reason why it has to be.
That's the reason why there's this closure property for monoids. So that same if you have a function, it takes two A's, it actually needs to return an A again. It needs to return the same data type again.
Maybe that's a little off topic, but with MapReduce, so you just told us how to change with map from words to frequencies. You can change the whatever it was, to a homomorphic function.
I mean, this is...
But you do this because, I mean, you use MapReduce because you want to have a performance increase, right?
Yes.
But if you change it now, don't you get all the runtime in the map part and the reduce part? Because then you have to combine all of the three.
That's a lot cheaper than the other way around. Like for example, if you think of this first example,
I'm not sure if it's
maybe not. Let's not use that example, but the word count example. So for example, appending 3 pages.
No, I mean here it's here.
Yeah, but it's the same thing.
No, because then you have 3 huge maps with all the information. Here
No, but you only have maps with words and integers.
Yeah, but here you
I'll tell you why we want to do that. If you have a really large data set, and usually we're talking about database indexes here. So for example, you have a lot of text and you want the count of the words in it, right? And then one page in the whole text changes. So if you would not have MapReduce, that would mean that you would have to recompute everything. But with MapReduce, you have to recompute just this one section that is changed words in it.
Yeah.
And also in the word frequency example, you reduce a list of words, a whole page, to a map with the word count. So you reduce the data.
No, but then you have the last step, and then you have all the information still, and then you have to add all the maps together. That's the same amount of work that you have in the map part. But the argument with just updating one byte, one map with data changes, that's a good argument.
I mean, I'm not sure how you would want to do it differently, other than like what would.
I mean, I don't want to do it differently. I just wanted the reason why it makes sense, because.
Yeah, but even if from a even leaving out that input, I think it's still a lot more expensive to add 3 pages together than to add maps together, because you're not. For example, if a word appears 100 times in the text, you actually have it 100 times in memory as well. Whereas in the map, you just have that word and the integer 100 in memory, and that applies for like all words. So I mean, I can't see how. And then you just add integers. So I really can't see how.
Yeah. Okay.
Yeah. Okay. So and there's I mean, on this page there's a nice explanation of how you. Sometimes you have operations which might not seem like you can use monoids on them, or like you can use them as monoids. Like for example, the average case, where you say, is this mine? Oh, sorry. The average, yeah. So let's go. Yeah. Okay. So here is the definition of average. It just takes 2 values and determines the average. Pretty simple. The problem with this is it's not a monoid, because it violates the closure property, and it violates, I mean actually it violates all properties, but so like for example the closure property, it takes 2 integers, but it returns a floating point number, because the average of 1 and 3 is 2.5. So it doesn't abide the closure property, and like some other properties as well. So let's not go through why it doesn't work. How you implement this is rather than dividing the thing up front, you just define a new data structure, and this is now the map part of MapReduce. Like you take the input and you map it to some monoid, and the monoid here would be a data structure that has a running total and a count of the arguments you've seen so far, which is like how you would implement an average function with an arbitrary number of parameters. And every time you just add 2 averages, you just update the totals and the counts. And now this data structure now is a monoid. And that's what you, if you want to use MapReduce again, this is the map part. And then in the reduce part, you just add 2 averages together again. Okay? So, yeah, I mean, does it make sense, or are there any questions? And like, there's a lot of use cases you can I don't know, imagine where working with monoids can increase your performance a lot. Because you, like for example, this, I mean, not only performance, but reusability. Like for example, this word frequency function. If I were to write this in Java, I would probably write different functions which do the same. One's for a document and one's for a page and whatever. and you just end up duplicating code a lot. Whereas if you write the function in a way such that it's